So I thought I'd finish up a project I've been working on for a while. Well, mostly it's been sitting in a box or a drawer. This is a microphone preamp designed for a headset, pretty special headset. I got it on the source of all things good and also Chinesium, eBay, and it is a H157 headset typically used by, I think, aviation equipment. This is actually a military headset. I think it was made by Sonotronics, which is a big supplier. Comes with a boom mic monaural headset, hi-fi quality, full 3000 hertz bandwidth, and all metal, little ball joint here, so you can sort of point this wherever you want. You can rotate this. It's got the passive noise cancelling microphone, and if you're not using it and you want to look cool, you can sort of pop it up like that. And reasonably comfortable to use, in fact, surprisingly. Yeah, but the issue with this is that the microphone, which can be swapped, you just pop this out. But the issue is that it's a 5 ohm microphone, and this is a, I think it said somewhere, doesn't say, it's an M101 element, and this is the 5 ohm version, which means that the output voltage when you're shouting into it is about a millivolt, and that's no good. So I had to build an amplifier because I wanted to interface it with something designed for 150 ohm. So we ended up with this thing, and we're going to take a look inside, but this is a shielded Chinesium alloy box. I've installed feed-through caps for all the inputs and outputs because this is designed for radio gear. So I've got power supply at 12 volts or so, it runs off 5 volt internally, and audio output, single-ended, and then the input here is technically sort of half-balanced, but the feed-through caps just stop any RFI getting in above about 100 kilohertz. So let's just take this thing apart and see what it looks like on the inside. I've kind of forgotten, so this will be exciting if I can find a screwdriver. Well, it's somewhere. We'll just cheat and use a flathead. That'll work. It's a somewhat interesting technique I've used here, if you ask me, then I'm pretty biased, of installing feed-through caps through panels, because they're designed to be soldered in. These aren't threaded, and they're 2.5 millimeter outer diameter. And what I did with the first ones is I put this piece of copper tape on the back and then soldered to that, and that actually holds them pretty well. What I found later is that if you're a bit careful with your drilling, I like to use a Dremel for that bit, very high speed and decent amount of alcohol as cutting fluid. You can actually cut the hole small enough that you can just force it in, and it tends to stay in place actually. So I've done that with another board, which I also didn't shoot any video on. So yeah, the same thing here, and didn't bother cleaning the flux off or anything because I'm lazy. And the board's in here, and it's installed in a very silly way because that's all I had available at the time, where I put some nuts in here, and then there's spacers, and then I've just drilled some holes from the top here. And you can see I missed a hole here, and because I was initially gonna heat sink the voltage regulator. Let's try to separate these screws because these are slightly different. They have built-in shake-proof washers or something similar. and the board should just fall out. There we go. So this was the first hack I had at a design like this. You see I bent and actually threaded that, but it's too soft, it's just copper, so it wouldn't really take a thread. Pin header input, RFI filtering, big coupling cap, and this is a, there's a little surface mount transistor there. This is built using a common base amplifier with something special. I'll switch to a narrow lens so you can take a look at the board. So here's the board in a relative close-up. I've switched to a 40mm now. What I've got coming up, I've got a macro lens in post, so I should be able to get better close-ups of circuit boards, especially when I'm doing surface mount. I also tried to stop down a little so I don't get too much, too shallow a depth of field. Anyway, there's it's a common base amplifier with an op amp over here for biasing, and instead of a collector resistor, this actually uses a constant current source driven by two transistors here as the collector resistor, and that means I can set a very high drain or collector current, which pushes the transistor into an area with high beta, while still maintaining a very high output impedance. This is very similar to a technique used in RF, where you put an inductor on the collector, typically, and that increases the gain significantly, while still allowing biasing without needing a very high supply voltage. And the input impedance is about 50 ohms, slightly lower when it's closed loop. And that's why I have such a big coupling cap here. Normally I'd get away with a 1 micro ceramic, would do it for almost anything, but in this case I want low frequency performance and as little high frequency performance as I can. This falls off at about 5 kilohertz. And it's closed loop as well. There's feedback, that's through one of these trimmers. I didn't actually label what they do. But I'll leave that one's the bias current, that one's the feedback, and that one's the DC operating point. There's a Darlington emitter follower for the output buffer into about 150 ohms, which is the intended load resistance. And the plan was to just get some pins, install this so that I can power it up and actually use it. So I'm gonna set about doing that. Okay, now I've got some wires soldered onto here with some DuPont headers, and I checked and these actually fit like that. Beautiful. And now I can just go ahead and solder the other ends, since I'll always be able to just remove that and then pull it out along with the other plate. So yeah, I'm just going to go do that, and I'll make a cut here. Okay, so that's one end soldered on. This is the audio output and the 12 volt power feed. So I think I will, it's fairly solid, but I think I'll just tack on some glue there to hold it in place. So let's just do that. So for gluing things, I like to use hot glue wherever I can, because it's really cheap and easy to use, and it has infinite shelf life. So I got this Bosch PKP 7.2 lithium, really cheap. The only trick I've really found to using it is to make sure that when it says it's warm, just wait a minute or so, because otherwise it tends to, you don't get the full heat out of it. So just tack on a good glob here. Because otherwise it tends to be a little too cold, and Save that for later. Too cold and doesn't really bond too well. But if you get the right temperature on the glue, then hot melt is pretty damn good. So I'll just let that sit for a minute, and then I'll just solder onto the other ends. So here's sort of halfway finished product. I just soldered on the other end, put some glue on stuff, glued here as well to stop this from snapping off at the joint. And what we can do now is just take these wires, make sure we get them the right way around. Pop that one on. Pop that one on. And it works, sort of. We'll have to test it now. Well, it's a good job I made this thing somewhat easy to disassemble. I turn it on and it pulls about an amp, which I think is actually the current limit of the voltage regulator. I checked and I didn't get the wires the right way. I think there's actually an issue with the circuit board because there's a little gold strip on the edge here. And thing is, there's a bit of a fuck up with the layout on this board, and that strip may actually be connected to 5 volt. So there's a good chance that's the issue. Let's see, I'll just pop that out. And yeah, I think that might be it actually. I'll have to look at this some more. Yep, just used the old snippers here and just cut some notches near all the mounting posts, and that seems to have solved the problem. So now I'll have to reassemble it. I'll film the reassembly for you, I guess. Anyway, one issue is you can pull it out, but you know, I still have to take all the screws out to and this is a little fiddly to get apart, but yeah, so it goes in like that, basically upside down, and then I can just put the screws in, preferably the right way up, since I already labeled this. So just get some reasonable approximation of in focus for certain values of in focus. If you're watching this on your mechanical television from the 1920s, then this will appear to be in perfect focus. And it helps if you get the threads right. There. Biggest mistake when assembling this sort of box is to just put one screw in and then tighten it, because it makes getting all the other ones in really difficult, especially when you're using the wrong screwdriver like I am. There you go. See, now they're all threaded, and you can just go around and tighten it up. And once we've done that, then we can go ahead and try to pop. Probably should have started with this, but never mind. That's one in. We'll do the other corner here. That screw's supposed to be a little offset. That was on purpose. It is threaded though. It's just the holes misaligned. Did actually countersink these so it would be relatively flat on the top. I'm not sure what I'm going to put this in. Probably just a plastic enclosure or something similar. So now, let's see, it goes around that way. Minus on the bottom. There. there, and wires sort of go in like that. And here's the tricky part, because you can't just set this down on the bench now, because if you do that, you crush the pins on the other side. So let me just put in 2 here, and have one immediately fall out. So I have to be really careful applying any downward pressure on this. That's one caught. There's the other, and keeping a steady pressure on this. There, and there. There we go. That's getting it. Assembled box. Okay, let's hook it up to the scope and try to get some measurements, eh? Okay, so I've made a little measurement setup now. I've got a signal generator coming in down here out of frame, and I've just used some DuPont headers to get power and signal into it. And I'm measuring the output voltage relative to chassis, and I'm applying 7 or 8 volts worth of power. Internally, everything's regulated down to 5 volts before doing anything. So let's just take a look on the scope now. Okay, so in blue is the input signal, and in yellow is the output signal. Now the scaling on the blue is 10 millivolts per div, and on the red yellow it is 200 millivolts per div. And I've got some measurements on the bottom there. I'll read those out for you. And we're using trace averaging because otherwise it's very difficult to actually capture the input signal. So I can turn down, and there's also some mistriggering occasionally. But basically, turn it up, and I'll show you the actual response later. But now we're putting about 17 or 18 millivolts in, and we're getting around 1 volt peak-to-peak output. This is at 1 kilohertz. I'm going to turn off trace averaging here so you can get a better idea of what's actually going on here. You can see that the input signal is just swamped in noise, and turning on the bandwidth limit barely does anything. I'll just reduce the scaling on that so it doesn't get too in the way. And we can reset the trigger down to 0 here. Basically, you just need a tiny amount of signal to get something usable. And the output swing is somewhat limited. It's better into, it's clipping asymmetrically now. So basically what I found is that even though this is not the ideal offset, I found that this gave the least amount of distortion in the active region, and this is sort of at maximum output. We're getting almost over 1.5 volts peak to peak out, and that's about as much as it can give. But normally you're going to be operating down here where the scope is actually having trouble capturing the signal properly. This is sort of a normal, typical output signal. I'm not sure what is causing this glitchiness here. I think it's very high frequency noise coming in from the probes. But yeah, this is sort of where it'll be at, sort of tens of millivolts, maybe up here. You're not going to be operating it up at 1 volt peak to peak for a microphone input. That's line level output where it'll start to struggle, but that was not the design. That was not a design goal anyway. So, I think what we should do next is simply plug it in to the camera and see what that sounds like. I'll try using the built-in microphone, and we'll see how that goes. Okay, I've got this thing wired up now, the camera, and it's looking like there might be some ripple on it, but on the signal. And I've hooked up the actual microphone capsule that I intend to use as well.
this is what it'll sound like potentially once I get it wired up into the radio I'm going to use for it. And there's a lot of measurement noise on the signal here.